Yeah, I think we can start now. I'll just give a brief intro. So, hello everyone to our fourth talk in this alumni talk series. Today we have Dr. Shadab Alam from the batch of 2012. So he did his PhD after graduation from Carnegie Mellon, and he is currently a postdoc at the Institute for Astronomy at the University of Cambridge. So he works in a lot of things. So galaxy evolution, galaxy formation, dark matter halos, and active galactic nuclei activity. And on the larger scales, he works on the large scale structures and the effects of dark energy and general relativity in cosmology. So I think I'll let him speak now. Yeah. Shadab, you can now speak. Continue.
Thank you. Thanks a lot for that nice introduction. Just one correction. I'm based at University of Edinburgh and not at Cambridge. And I'm very excited to be here. Thanks a lot. It's all right. Thanks a lot for this invitation. I was not quite sure how to make my presentation for this particular group. And so what I thought I will do is I will generally introduce what are the kind of things I worry about in a day-to-day life, including a few things about my time at IISER. And hopefully this will not be too long so that we have a time for conversation so that you can ask questions and it will be more of a two-way conversation rather than me speaking most of the time. So let's see how it goes. So first of all, let me give you a brief overview of my current status. I'm a postdoc at University of Edinburgh, which is situated on a beautiful mountain, the Royal Observatory, which you can see at the background of this image I have with my son. And yes, I'm a new parent, so I have a 10-year-old son, which takes most of my time, especially basically whenever I'm not working, I'm doing something with him these days. In terms of work, so I particularly focus on galaxy redshift survey, although I work on other kind of surveys as well in combination. But my main focus have been galaxy redshift survey. And so what are these galaxy redshift survey? You can see a video playing on the top right panel, which is actually coming from real data from a survey called Sloan Digital Sky Survey. What you're seeing in this video is location of individual galaxies as measured in our universe. So it's our local universe. And for each galaxy, we have three-dimensional location of the galaxy. And that is something actually expensive and hard to do, precisely because these galaxies are at distances which is cosmological in nature, in the sense that these are really, really far away. And so the difficult part to do these surveys is always to measure distance of these galaxies. It's kind of easy to measure where they are in the sky, because you pretty much have to take an image, although this image has to be taken from big telescopes. But then it becomes difficult to figure out how far they are in the line of sight. So are these galaxies in our neighborhood, or they are like really far away, or they are in really early time of the universe? And so that requires us to measure redshift, and that's the only way you can measure distances, precise distances to cosmically far galaxies. So in order to measure distance, I guess most of you are familiar with the spectrum, and you probably have done some or other course about emission line and absorption lines, so quantum mechanics, right? So what you really have to do to measure these distance, you have to measure spectra, which is essentially taking light from individual galaxy and spreading it across wavelength, and you want to measure flux as a function of wavelength. And this is hard because you have to take one galaxy at a time, pass its light through a prism, spread it, and then do that measurement, which is many more steps compared to taking an image of a galaxy, right? And so this requires pointing optical fiber to each individual galaxy. And so if you want to do it for a million galaxies, you can imagine you have to do it a million times. And so you can't do one galaxy at a time. There are, in in early 2000, essentially, there were developments which are called multi-object spectrograph. So you can measure multiple galaxies at a time. And so Sloan Digital Sky Survey is one of the first one or leading one, which has done this over last 20 years, actually. And in 11 years, last 11 years, it has measured more than 2 million galaxies. And so this is an image which is showing a small fraction of all the galaxies measured through this process. So that is the idea of Galaxy Redshift Survey. You need to measure redshift for individual galaxies. It's a very painstaking job, because how Sloan Digital Sky Survey did it is basically has a aluminum plate in its focal plane, and every time you want to see a particular part of the sky, you point to the sky. You want to figure out where your galaxies are in the focal plane and drill a hole at each of the location. It can do 1,000 spectra at a time. So you drill 1,000 hole, then you put fibers depending on when and what part of the sky you're observing. And then you let your instrument run. So you can imagine you need to do 1,000 galaxy at a time, and then you do 1,000 times, that's million. So 1,000 plate will give you million galaxy. So if you want to do 2 million, you have to do 2,000 plate. And so this is why this has taken like something like 11 years. Right now, so Sloan Digital Sky Survey is kind of over as far as cosmology is done, although the telescope is still being used, and there's a lot of interesting other aspect of science it's going to do. But the current leading galaxy redshift survey is what is called DESI, or Dark Energy Spectroscopic Instrument. So this is where most of my time spent these days. I'm working in DESI and making sure we are ready to do the analysis once we have DESI data. So DESI is something which haven't started yet, and you can see the in the top left building of DESI, which is stated in Arizona, and the telescope beside that. Now, the difference between Sloan Digital Sky Survey and DESI is that now DESI, in place of having this aluminum plate in its focal plane and you have to drill hole, it has robotic fiber arms. So it's fiber arms which can move through electronics, right? And so you don't have to go and drill hole. And it has 5,000 of them at a time. So it's much bigger instrument, as you can imagine, rather than 1,000, 5,000. And the plan is it's going to observe something like 35 million galaxies in the next 5 years. And so it's going to really, the data is going to blow us apart compared to like 1 million galaxy to 35 million galaxy in 5 years, covering much wider redshift, much wider type of galaxies. We are really excited to see early DESI data, and hopefully this will happen as soon as early next year. We'll already have what is called survey validation of DESI. So, yes?
I have a question. So,
yeah, sure.
So what is the typical exposure you need for such surveys? Like you need to have good measurements for spectra?
Mm-hmm. That's a very good question, and that requires, in fact, lots of effort and time in figuring out what is it. It really depends on what is your instrument size. So, for example, Sloan Digital Sky Survey was done with 2.5 meter optical telescope, and it observed relatively bright galaxies. So if you have bright galaxy, you'll need shorter time. So for something like that, it used to do exposure of half an hour for most of Sloan Digital Sky Survey galaxies. For DESI, it's a 4 meter telescope, so it's a bigger telescope. You can do shorter, but it's going to observe fainter galaxy. It's going to also observe different type of galaxies. So there's a term called different type of target selection. And so when it's going to observe brighter galaxy, it can do something in 10 minutes. But if it's going to do fainter galaxy, then it might have to observe things for 30 minutes. It's also a question about what is the condition in the sky. So sometimes the sky is really dark, in which case your noise is very low, and so you can actually get away with shorter exposure time. So there's a whole lot of software development and analysis which has been done for DESI in terms of figuring out what should be the exposure time for different tracers, and it's going to be actively changed, but it's of the order of 10 minutes or so for most of the observation, which is in the dark time and relatively brighter sample.
Okay, thanks.
All right. So That's DESI, and that's where most of my time goes on. In terms of science interest, I have a broad range of science interest, as it is describing in the introduction. But I just wanted to show you one this image briefly. What are the kind of thing I think about? So some of the thing I think about is about the cosmic dance, what I like to call. It's essentially saying that these galaxies are not stationary. They are interacting with each other like humans interact with each other, right? And the obvious way galaxies will interact with each other is the gravitational force. And hence, they are experiencing each other gravitational force. So if you keep two galaxies and nothing else, then they are going to attract each other. And so there is going to be velocity. Both of these galaxies are going to have velocity, and they will just inflow into each other, right? But given the universe is complex and there's millions of galaxies, all of these galaxies are interacting with each other, and there are all sort of gravitational interaction leading to velocities of these galaxies. And so these velocities affect your spectra. So this leads to something called redshift space distortion. I will not describe in detail, but if you ask me to describe it, I'll describe it later in the talk. And what that leads to is a pattern of cosmic dance, which is shown in the this inset in the bottom left plot. This is called redshift space distortion. Just take it as some sort of a pattern which is imprinted because of these velocities. If you are curious, I'll tell you more about it. And that's one of the main focus for my PhD, in fact, and I still continue to work on that, and that will be one of the main science case for DESI, which is going to tell us various things about universe, as well as testing general relativity. So with that, let me come back to this important point I wanted to raise in the beginning, is about the work-life balance. When I was at IISER, I never really heard this term, but I feel like especially it might not resonate with you right now, but especially if you're in the final year and you're going to go either in a job or industry, do actively think about work-life balance, and that's very important especially if you're going in the science, because things can get very difficult very quickly. And so there's a funny image of me trying to strike a balance on a stone, but right now I'm still struggling and trying to have a work-life balance with being a new parent and working in active field. And one of the best kind of investment you can do, especially if you're going to start a PhD in an isolated place anywhere in the world, is to try to invest in yourself along with your science interest, right? So that's essentially my overview, and let me go and describe a little bit more in terms of how do we analyze these things, or how do we analyze a large-scale structure. So what is the current picture of the universe? Let's look at that. If you have heard about any cosmology talk, I'm sure you have heard this word inflation, right? This is something about the early universe. I'm not going to get into that. But after inflation, what the universe looked like, it is essentially it's full of quantum fluctuation, and there's no structure. Everything is uniform, but there are small fluctuations everywhere, which is what is represented in the top figure here. Right, there are essentially noise. Now, if you let that sort of field be there, and the main driving force is gravitation, then what's going to happen is that anywhere where you have a higher density in these fluctuations, and given certain condition, what is called gene stability, is going to collapse, and it's going to form a bigger and bigger higher density. Anywhere which is under density, it will become a vacuum and become a bigger and bigger under density. And so a field like that is going to evolve and will make something smooth. So that is what's shown in the bottom panel here. In terms of like the gravitational potential of the universe, you'll form these big potentials at several places, and then you'll form large-scale structure. And this big potential is what is called dark matter halos, because they are essentially collapsed objects made up of dark matter, but there's no, we don't really know what the real physics happening there. And in these dense regions, which is called dark matter halos, you'll have really high pressure and high density. And if you start putting in baryonic matter, the kind of matter we are made of, then they will show all sort of baryonic physics. You'll see nuclear physics, which will lead to formation of stars, and then finally galaxies. And then it will form various kind of galaxies. This is still active research topic, like what kind of galaxies, where it's going to form, and what happens if you put in black hole there. If you have a black hole at the center of galaxy, what else you need? Sometimes we see galaxies with jets coming out, so these are called AGN or quasars. What is really driving those AGNs? Are these galaxies special compared to everything else? And so these are some of the active research questions, but eventually you'll form all of this, right? And now if you want to measure this, what the basic question you want to ask is that if I just look at the structure in the universe, is it going to be something showing some structure, or is it some random distribution? If you remember from the video, when you were seeing the galaxies, they didn't really look random. They look like they were very strongly clustered, or there's nothing there, right? And so there's a structure in this. And so one of the popular way to measure this structure, there are several other ways as well, but one of the popular ways to measure two-point correlation function. So what is really the idea of two-point correlation function? It's fairly simple. What you really want to ask is, if you take 2 points of any kind of source, for example, galaxies, and you try to measure distance between a pair of galaxies, and then measure it over all of your sample, basically every galaxies you have, what are you going to find? If it's a random distribution, then what you should find is that it really just sample the volume, in the sense that if you take 2 points, then the distance between them, and if I just count how many pair of galaxies I find as a function of distance, it should sample the volume of the cell, right? But if there is a structure and it's not random, then you'll find some different structure which is imprinted in that. And this structure is what is sensitive to basically every aspect of cosmology, including how the gravity works. And this is what we try to measure with Galaxy Redshift Survey. And then we try to model from our best theoretical understanding to finally constrain various aspects of cosmology. For example, what is the curvature of the universe is something you can constrain by looking at structure into two-point correlation function of galaxies. All right, just to give you a little bit intuitive idea, if you want to think, especially if you are hearing about two-point correlation function for the first time, let's say everyone in this meeting, if I was giving this talk in a room in IISER, imagine that situation, and all of you are sitting in a benches, and if I ask what is the two-point correlation function of the audience, then what you'll find is that at very small separation, there is essentially no pair, because none of you are sitting very close together just because you have a physical size. And typically, what you'll find is that the size of the bench, or the half of the bench size, you'll find a lot of pair, because most of you will be sitting in the two edge of the benches. Also, the separation of the bench along the depth of the room versus length of the room. So there's going to be various scales where you find lots of pair, and everywhere else there will be zero pair. Basically, there's no pair of audience member sitting at those locations. And so what you'll see is that you'll not find some sort of random structure, you'll find a very coherent structure, and from that you can infer what is the size of the bench, what is the different distance between the benches, and things like that. You can actually infer by looking at such a correlation function. If you take it to a slightly different scenario, given coronavirus is really high in the world right now, suppose you're in again sitting in a room, but with coronavirus restrictions, which is saying, let's say, we have a restriction that nobody should be anywhere closer than 2 meters. But we also want to pack maximum number of people in the room, so everybody is going to be at the 2 meter distance sitting with each other. And if you really follow that strictly, and let's say in such a scenario, if you were to measure two-point correlation function, what are you going to find? And the answer is going to be very simple. If you're going to measure that, then anything below 2 meters, you'll find zero pair right? So you'll find no pair of people sitting anywhere closer to 2 meter. At 2 meter, you'll find this huge peak because most of the people are sitting at 2 meter. But if you and then if you go beyond 2 meter, now you'll find the higher modes of the organization. For example, if people are sitting in a grid pattern, then you'll find that if you imagine a square of 2 meter, then you'll find the side diagonal, which is square root of 2 times 2. You'll find a lot of people sitting at that distance, and then there's all sort of higher modes of that. So if there was a grid structure like that in anything, and you measure 2-point correlation function, you can learn a lot about that grid without really knowing that grid in advance. So that's the intuitive idea of 2-point correlation function, and we use it a lot for either galaxy formation studies or anything to do with the cosmology, right? So if you come back to this, then these are the main question which I worry about in terms of looking at dark matter, looking at various kind of galaxies, is how do we really predict what are the galaxy properties? If you look at a galaxy, then you can find a galaxy is either red and dead, which is called something elliptical galaxy, or galaxy is actively star forming, so they look bluer, or galaxy have a active black hole, and so you'll see a jet around it. So how do we predict these galaxy properties? Like, how do you know? And it's very involved and difficult problem for various reasons. Other thing we also worry about is that with respect to dark matter, so if there's a dark matter distribution, what is the relation between galaxy and dark matter? And this is something we can only infer because we don't directly see dark matter. But there are various effects which help us estimate dark matter in various parts of the universe. And so what is the connection between galaxies and dark matter is something is still a very active research topic, and that's also known as galaxy halo connection. And there are various detailed questions about if there is a cosmic structure, what is the role of that in terms of galaxy formation. In terms of cosmology, everything you describe, right, in terms of the fundamental theory is actually about dark matter itself. It's very hard to write a theory for galaxy because it's a complex process with all the magnetohydrodynamics and all the complex physics built into that, and that is something you can't solve very easily. And so everything we describe in our modeling scheme is pretty much more or less about dark matter. And so if you look at different type of galaxies, how do you map that dark matter distribution or correlation function for the dark matter to the galaxy? And will it matter? Will you get different answers about the universe if you were to actually select different kind of galaxies? And so that's actually a big worry for all the Galaxy Redshift survey. And how do you go about it? Can that bias in terms of what you're going to infer about the content of the dark energy or dark matter if you're to look at AGN versus a star-forming galaxy? And so these are like broad questions. I just wanted to put this out. Is something I worry about. If you want to ask about any of these things in more detail, I'm happy to discuss, but I feel like it's important to know questions, more important to know questions so that you can go and explore about those questions later on. So I'll slightly switch gear. This is all about cosmology and galaxy formation, but now I wanted to come back a little bit to physics. If you were to see an image of Hubble deep field, so this is actually an image from Hubble deep field, you're seeing this beautiful color, right? And when you look at an image like that, one question I wanted to ask is, like, is this true intrinsic color of these galaxies what we are seeing, or is something else? Is the color of light intrinsic? And so this will require you to think about if there's a galaxy which is emitting light, that light is traveling all the way through us, depending on how far the galaxies are. And so there's a lot of physical phenomena which could happen, which this light will experience. And all of those physical phenomena are going to influence this light, and hence the color of the light. So once you start thinking about a journey of a photon from a faraway galaxy to us, you'll realize that there's a lot of interesting physical effect which could happen, and you could try to learn that. And hence the true color, the color we see is not really intrinsic color, it's all all mugged by everything these photons goes through and interact with. So that brings you to a lot of plethora of interesting physics. And let me show you, for example, this image. It is trying to represent that there are two dark matter halo. In both of those dark matter halo, there are galaxies, and these are emitting lights. Now, as the light is emitted by these galaxies, they are going to, first of all, climb the potential veil of the dark matter halo, and hence it will change its wavelength. Then, it's because the universe is expanding, the expansion of the universe will have an impact on the wavelength of the light, and hence the color of light. Things like that is going to happen, but there's actually a lot of these effects, and these are very interesting in my opinion. And this is what I call the physics of astronomical light. So this is really, each one of them is a very simple physical process, which is very interesting to study. So I just listed a few, and these are the kind of effects I worry about and try to detect. I've worked in several of them. I've worked on redshift space distortion, weak lensing, ISW, gravitational redshift, relativistic beaming. And these are very hard and intricate to measure, in fact. So, and there are many more. Okay, and so I'll not describe all of them, but of course you can ask me if you are interested. But let me describe just one of them, which is called gravitational redshift. This has a very nice history associated with it. But essentially, what the effect is, if you have a light in two different gravitational potential, if a light is traveling across it, then the gravitational potential is going to have an impact on that, right? And so this is what is shown in the top plot, that if for example, the representation is if you have a sun and light is emitted from the surface of sun, then as you move away from the sun, the gravitational potential is going to change because of the sun, and hence the light, the wavelength of the light is going to change. So this effect, because of the gravitational potential, the change in the wavelength of light is called gravitational redshift. So that's the example of the sun, and that is where it was measured for the first time in the light coming from the sun. But if you imagine galaxies, the galaxies are generally assumed to be in a dark matter halo, and the dark matter halos are really massive objects, so they have huge potential. So as the light comes out of this dark matter halo and start traveling towards us, it's already going to shift by a certain amount, and this is something you can measure. In fact, we have written a paper 3 years ago showing one of the first measurements of the large-scale structure of this effect called gravitational redshift, which has a few complications to it. And then you might want to ask like any of these questions in detail, like how do we observe galaxy, how do we observe dark matter, how do we deduce cosmology, and what about the role of black hole AG in galaxies in the cosmological inference, and how do we measure gravitational redshift, for example. I'm happy to address any of those. But let me, since I think, okay, so it's already half an hour, so let me just briefly comment on my time at IISER. I was actually yesterday, I was trying to think of what I did at IISER, and it was hard for me to remember. It's already quite a while ago, and so I found out my old website. I was surprised, and I was laughing at myself. We can see the link if you want to have a laugh. You can have a look of myself, which is describing all my projects and blah 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 and that. And by reading some of my own report, I felt like I was really a silly and naive with not much communication and writing skill. I found that I wrote a report on honesty and integrity, and it was like, really, it's really funny for me. It's really silly, actually, if you want to read it. But I felt like one thing, if I would tell about myself, is that I was never afraid to ask questions, especially silly questions. I mean, this is being told several times, but I would like to just repeat it. Yeah, I do ask questions independent of how you feel. It's not a good idea to think about what kind of question it is. As long as you're curious and you're interested to know the answer, yeah, you should ask question. These are some of the big ideas which influenced me during my time at IISER. I was really in kind of love with the algorithm, and Turing machine was something fascinating me. In fact, I gave one of the first talk in Science Club of IISER on the journey of Turing machine, and like what is the idea and things like that. Later on, during the electronic course, again, I was very fascinated with all the idea of control system and how electronics can allow you to control various very complex systems. And finally, I was introduced with radio astronomy in a course which I audited, and I didn't even took it as a credit, aperture synthesis, and this really made me think a lot and kept me fascinated for quite some time, like how really the issues with large wavelength is such a big issue, and then how people have solved it with this idea of aperture synthesis is something amazing. If you haven't heard about that, definitely I will suggest googling that. In terms of project, I did a wide variety of projects while during my time at IISER. I started with working on fractals and presented a poster in SINP Calcutta on fractals and how do you generalize it. So in fact, one of my colleague, Mohammed Zuhair, we wrote sort of a small, not really a paper, but a note, which we presented there. It was about, the idea is about how do you generalize fractal and make fractal of any dimension in a n-gon. It was a nice mathematical treatise. Then I did a project in radio astronomy. Then I moved back to condensed matter theory, which I worked in HRI. Then I went to Pune University to do a nanoparticle synthesis. I think it was BFO, bismuth ferrite, which was a hot topic at that time. So it was actually synthesis in the lab and characterization, so real instrumentation there. Then I came back to radio astronomy with aperture synthesis and interferometry. I also did a project on computational fluid dynamics, looking at the Couette flow between the two sheets of things and trying to model that in a computational way. And finally, I did my master thesis in radio astronomy. Then at the time when I finished my thesis, I was interested in either computational fluid dynamics or radio astronomy. I applied to a few places in US. And I got this offer from CMU, where there was a good cosmology group as well as cosmology and astronomy group, but there was also a radio astronomy person, which is why I mostly went there. And there was a good computational group there. But it turned out the radio astronomy person I wanted to work with was not taking student at the time, so I had to joined my advisor, Shirley Ho, who was working on more optical astronomy, but I really enjoyed that field, and so I continued working on that. I finished my PhD in 2016, and then I've been at University in Edinburgh since then, so last 4 years, doing my postdoc here. And then I already told you what the kind of things I worry about these days. So I did write in my abstract. I will also briefly mention this is an image, an equation from my master thesis, in fact, showing you a dish antenna from JMRT, which is marvelous. If you haven't been to JMRT, I must say you definitely need to visit if you're interested in any aspect of astronomy. It's a golden opportunity. You're so close to JMRT. The right one showing the pattern of antenna. And what is fascinating about radio wave and interferometry is that radio wave, of course, it's a large wavelength, and so you are diffraction limited, so lambda over d. So if to really get a good resolution, you need to have very, very, very large dish. But that's practically impossible from an engineering point of view to get a very precise resolution. And so people have came up with these ideas that in place of having one dish, which is measuring the full image, which is what we do, how about if you take a pixel of the image and measure that with two different locations, dish separated by a certain distance, And so you really construct an image by pixel, and there's all sort of technique involved in the Fourier space, Fourier analysis. And in the bottom, I'm just showing you Van Sittard theorem, I think that's what it's called, which is showing you how an image in real space is related to its Fourier component, and then how you can measure various component of that and finally reconstruct this image through aperture synthesis and interferometry. I think it's still my number one idea so far in terms of astronomy imaging techniques. So this is kind of my last slide, a little bit about my extracurricular at IISER. When I joined in 2007, there was essentially not any club at IISER, and so we started thinking about, in fact, an astronomy club we wanted to start. But it turns out there's not enough number of people who will be particularly interested in astronomy, and so we decided to start a science club rather than astronomy club. So I was involved with science club all throughout my time at IISER. We started this idea of organizing things on Science Day, which used to be organized by Science Club at that time. I don't know what's the case now, but we started various kind of events during the Science Day. As a part of Science Club, we of course organized field trip to GMRT and Gravity, which are a lot of fun. I'm sure you have heard of Mimamsa, given you're in IISER Pune, which was again started by Science Club to begin with. I don't know if it's still managed by Science Club or there's a different group, but it was quite fun. And during my first year, during the first time when we were organizing Mimamsa, it was a very small event. It was only within for colleges within Pune. And 2 days before our preliminary round, we were still struggling to get at least 5 teams, because we wanted to have at least 5 teams so that we have 4 teams for the final. It was quite a struggle, but now it's a very big event, so I'm very pleased to see how Mimamsa has grown compared to how it started with. I participated in a few play in Carva. As an extracurricular, this is not part of any project. I actually tried writing a molecular dynamics code, which I didn't succeed in, but it was fun to explore. We used to play a lot of sports. I was very bad at cricket. I was reasonably good at volleyball. But apart from that, we also used to play a lot of computer games. So Counter-Strike and Age of Empire, if you're familiar with, used to be our fun thing to do. So with that, I will stop, and I will stop with this slide again where I list a few questions. Yeah, so thank you. Sorry, it took longer than I thought I will take for this description.
There are questions in the chat. So if anyone wants to ask them, they can unmute, or I'll ask them.
Hello, I have written the question in the chat box. This is Ajay.
Hi, Ajay.
Yeah, so I want to ask the research technique between the optical and the radio astronomy.
Sorry, what technique in optical and radio astronomy?
So I don't know much, but I'm just asking what is the difference between the optical and the radio astronomy. So.
Okay, so that's a very good question. In principle, if you think about it, it's as far as observation is gone, in principle, there should not be any difference in the sense that you have a telescope, you collect light, and you collect light at different wavelength. But technically, there's a lot of difference because optical is has a small wavelength, right? And so because of the diffraction limit, your resolution is always limited by lambda over d. Where d is the size of the telescope. So if your lambda is small, you can actually have very precise measurement or very precise image. And so in optical, you don't really have to make very big telescope to get a very high resolution. But once you come to radio wave, the wavelength is very large. And so, for example, if you're thinking about meter wavelength, and so resolution, lambda over d, is very poor, even for very big telescopes. Something like GMRT single dish is 45 meter, which is much bigger than most of the optical telescope. But still, your resolution is going to be very poor. You'll not be able to see any small object at all. And so to really resolve it, you need to make very huge disks, or you need to use this idea of aperture synthesis, which I described, which is a collection of radio telescope you have to use. So that's on the observation side. It's a very different way to observe things in radio versus optical. Apart from that, now from the physics side, there is a large difference in radio and optical in the sense that you need to think about what processes is going to emit light in wavelength of radios and what process is going to emit light in optical. So most of these baryonic physics processes are very bright in optical, right? But there are various processes which are actually not very bright in optical, but very bright in radio. For example, anything to do with the synchrotron emission, if you have heard of that, where you push light through plasma and electrons. And so those are the things very bright in optical. There's also this idea of H1 line, which emits light in radio versus optical. So yeah, there are two aspects. One is the observation side. Techniques are very different, but then you also need to think about the physics side. And some physical phenomena is only visible in radio or bright in radio, and some are bright in optical.
Yeah, thanks.
I have a question. So, how do you differentiate, like when you observe a galaxy, how do you know if it's the gravitational redshift and what is the Doppler shift?
Right, so that's a very good question, and you can't differentiate that from an individual galaxy because all you're measuring is redshift, and that redshift will have everything it has gone through, right? So it will have the impact of expansion of the universe, which is the redshift. It will have impact of the fact that the light has climbed the halo, which is the gravitational redshift, gravitational potential. It will also have impact, for example, if the galaxy was moving towards you, then that will have an impact on that. So you can't really separate these things out. Also, the amplitude of these things are very different. For example, the dominant term is the redshift, which is due to the expansion of the universe on these galaxies. The second order effect is the effect of the velocity, which is redshift space distortion. And the gravitational redshift, which is order of magnitude is smaller than redshift space distortion, which is due to velocity. So really, this is tiny effect. So you can't differentiate between these things on an individual spectrum. And so you have to come up with some trick to measure this in some sort of a statistical fashion. And so the way we did it in large scale structure is saying that, let's say if you have a collection of galaxies for which apart from a redshift, a gravitational redshift, everything else is same. If that is the case, you can take these galaxies and subtract the redshift of one from another, so that the only thing you'll be left with, everything else is same, which means if they are roughly living in the same redshift, so the expansion of the universe is same, they have typically the same velocity, then all you'll be left with is the difference in the gravitational ratio. And so that, in fact, that is what we measured, is by subtracting from a sample of galaxies, by subtracting one set of galaxy which we expect living in a bigger dark matter halo and has larger gravitational redshift versus another set of galaxy which is living in a smaller dark matter halo and smaller redshift. And if you have something like that, then you can measure the difference, and that should be the difference in the gravitational redshift of the massive halos versus low mass halo.
Okay, thanks.
Hello, sir. I'm Kanishka.
Hi, Kanishka.
Sir, I wanted to ask, how do we observe our dark matter, and if you could give an insightful idea into what exactly dark matter is?
Yeah, that's a very good question. So as I mentioned briefly before, that we don't really observe dark matter directly because it doesn't emit any light, but we infer dark matter indirectly. So one of the most popular way to infer dark matter is what is called gravitational lensing. So if you have a source of light, a galaxy in the background in a far away, and if there's some sort of dark matter blob in front of it, then the light from that galaxy is going to experience this gravitational force from the dark matter, and so it's going to bend. right? And that bending is going to imprint a pattern in the light emitted by galaxies in the background. So that is called gravitational redshift. That's one of the way to measure dark matter in a faraway galaxies. In a nearby galaxy, there are a few other ways. For example, you can measure rotational curve, which is saying that if you have galaxy, if in a region, if you have velocities of the galaxies, then you can estimate, given the velocity, what should be the mass enclosed in that region, and that mass is mostly coming from the dark matter. Right. So there are several indirect ways to measure dark matter. There is no direct way to measure dark matter. There are few lab-based experiments. For example, in LHC, people have tried measuring dark matter by colliding a particle and see if there is anything there. So that's from the particle physics side. In terms of what is dark matter, I'm not sure we know the answer yet. There are several theories and postulates in terms of what should be the particle nature of the dark matter, or it's a field. So I'm not sure I can give you, I can tell anything new there. But what we know for sure is that we know what should be its collective behavior in certain scenario, because that is something we observe. So we know what should be the interaction of dark matter with light, more or less. We know that the dark matter should be pretty much very weakly interacting with baryons. So we know its interaction either with baryons or light, and we have been measuring that more and more precisely. And we know roughly what fraction of the matter should be dark matter, but we don't know the true nature of dark matter yet. And that's the big question. That's the $1 million question. In fact, that's why we are doing this experiment called DESI, which is going to happen in the next 5 years. Sorry, I don't have a more precise answer to that.
Yeah.
Hi. So looking at your projects, it seems that you had a lot of, you had interest in many fields in physics. So how if someone is interested in many fields in physics, then like how can one look for projects
Yeah, that's an interesting question. And in fact, so I feel like if you have interest in many fields in physics, it should be very easy for you to find project, right? So what I did during my time at IISER is that I essentially looked at whatever is available and just chose the best one. Because I had interest in wide variety of field, I didn't worry about like, okay, I need to work in condensed matter physics or astronomy or anything like that. Whatever is the best opportunity you think, both in terms of advisor, like how you feel about working with a particular advisor or the lab or a place, anything which it can be something as simple as, for example, as Ramana said, right? He went to UT just because the location was great and he was anyway interested in that kind of thing. He was interested in wide variety of physics. So I feel like if you are interested in many things in physics, then just look for any one thing which clicks with you, or just look for best opportunity, and you'll find a lot of options in that case.
Thanks.
There is a question in the chat. So Ajay Agarwal is asking if.
Yeah, this is my question.
Yeah.
So I want to ask that if one has a PhD in radio astronomy, can he go for the other field of astronomy, like optical astronomy or any other?
So if you have done a PhD in radio astronomy and then going for other field of astronomy,
for like optical astronomy, and like we have the X-ray astronomy. So can he?
So let me give you the truth here. In principle, when you do a PhD and when you're looking for a postdoc, so postdoc is kind of a position where the advisor have some sort of funding to do some very niche project, and they want people with experience, right? And so in that case of scenario, you will probably be kind of suitable for the project where you already have experience. And if you have done PhD in radio astronomy, you'll probably be more suitable for radio astronomy postdoc. And so you'll kind of continue to work on that. So I think it's a post PhD for your first postdoc at least. It's very hard to switch field because the selection is biased towards your experience, and so you just can't jump into another thing where you don't have experience in that case. Having said that, most of the postdoc offer you 50% of your time spent on a project which is predefined and which is being funded, and 50% of time of you is something you can work on you are interested in, right? And so if you're really interested in, let's say, optical astronomy, you'll still go for a postdoc, which is more 50% you'll be working on radio astronomy, and you can explore, you can use half of your time to explore what aspect of optical astronomy or any other things you are interested in, and at least develop some skills and experience so that for your next position, next postdoc, you'll be able to find a thing which is going in optical astronomy. So in principle, it's feasible, but it's hard. In the longer term scenario, if you're not just thinking about postdoc, but let's say if you continue your PhD in radio astronomy, you continue your postdoc in radio astronomy, and then you go and you find a faculty position. Once you have faculty position, now you have a lot more freedom, right? And so now you can essentially go in any radio astronomy or even broader things once you have faculty position in terms of long term. But it's not very easy to switch just right after PhD.
Okay, thanks. Yeah.
Sir, I wanted to know the scope for astrobiology.
Code for astrobiology, sorry. Did you say code for astrobiology?
Sir, scope for astrobiology.
Sorry about that. Yeah, I didn't hear that clearly. Scope for astrobiology. There is a lot of interest in astrobiology, especially in recent time, and this is because I'm not sure if you have heard of the fact that there is a mission called Kepler mission. It's a satellite mission. And so something like 5 to 8 years down the line, we were aware of very few exoplanets, so planets which are outside of for solar system. But after this mission, Kepler mission, we found lots of exoplanets, and now there are new missions, various telescopes, and there's a lot of funding to search for exoplanet. Once you start finding this large number of exoplanet, the scope for astrobiology have just grown humongous, because what are you going to do with these planets, exoplanets? One of the main focus is trying to find a signature of their atmosphere and signature of life on that. So in recent past, last 5 to 8 years, I would say, in terms of the funding, which is what drive the scope for astrobiology, have increased a lot. But more broadly, exoplanet research or planetary research, the scope for that have increased broadly. So if you are interested in exoplanet and astrobiology, I think that's a combination where there's a lot of opportunities coming up. You might see a lot of advertisement for both PhD position and postdoc these days for that field.
So if I could know that what I had to do to get into astrobiology?
What you had to do to get into astrobiology? I'll answer this in 2 parts. I think it's a very important question, and I personally I definitely asked this kind of question when I was at IISER, what I had to do to get into something very specific. But I felt that the answer was you don't want to really, although you're sure, kind of you feel that you really want to do astrobiology, you probably don't want to hang up on that idea, and you just want to do things which interest you, and like really do an interesting project which interests you. If you do that, if that is aligned to your astrobiology, most likely you will find a PhD position which is aligned to astrobiology, or in a department where there's a lot of people working in astrobiology, because that's what they look for. When you apply for PhD position, they look for what are your experience, and if it is aligned, then you'll get that. And so once you get that, you'll get a springboard to be launched in astrobiology. But if you don't find, let's say, it's feasible to do project in astrobiology just because there's no one in IISER working in astrobiology, if that's the case, or anywhere around, then it's not a big deal, because a lot of departments are very versatile. And so whatever closest thing you can find to astrobiology or whatever is your interest are, you should just try to get involved and explore that. Yeah, sorry, I don't have a precise answer, but I feel like it's not the right question to, not that it's a bad question to ask, it's not the right question to ask. The right question to ask is that how do you explore the things which you're interested in, right? And hopefully if you do some projects which is relevant for astrobiology, you will get a springboard and you'll automatically get into the field.
Okay, sir. Thank you.
Could you talk about redshift space distortions? You had said that you talk about it towards the end.
Yeah, sure. Let me see if I can pull out the slide. So as I said, redshift space distortion is about essentially this dance of galaxies and in their environment, right? So are you able to see my screen? Let me see.
No, not. I can't see the screen.
Okay, can you see my screen now?
Yes.
Okay, so when you're looking at these galaxies, one of the fundamental dogma of cosmology is that universe is isotropic and homogeneous, right? At large scale, of course, because at small scales all of us exist and we are not homogeneous and isotropic. But at large scale, universe is isotropic and homogeneous. And so when you observe these galaxies, especially when you observe the redshift of these galaxies, the first thing you're going to see in those redshift is the shift in these atomic lines or molecular lines, which is due to the expansion of the universe. The second thing, if the galaxy is moving towards you or away from you, then what you'll see is something equivalent to Doppler effect. So if, for example, if a train is passing towards you or away from you, you'll see that the sound waves changes its frequency. Similarly, the light waves changes its wavelength, right? And so that is the term which I am showing you. The observed redshift will have this expansion of the universe, cosmological redshift, plus this velocity term. So depending on how fast these things are moving, you'll see a small shift in that. And then plus gravitational redshift, which is shown in ZG, plus there are higher order terms. There are quite a few other effects, right? And so each observed redshift will have cosmological redshift plus peculiar velocity redshift. But this is only along the line of sight, because that is the only component you're going to be sensitive to. So the true 3D velocity of this galaxy is something you don't know yet. Now imagine if I were to measure this two-point correlation function I described you earlier in a sample of galaxy. Now this two-point correlation function, given the universe is isotropic at large scale, this two-point correlation function must be isotropic if you really can measure it. But because the line of sight redshift is going to have this velocity component, and hence your line of sight distance, what you're going to infer for this particular galaxy, is going to be biased. You'll not estimate the right distance, you estimate distance plus a velocity term. And so if I were to measure two-point correlation function such that I will ask the question, how many pair of galaxy I find as a function of distance along the line of sight, and how many pair of galaxy I find distance perpendicular to the line of sight, then what I will see is that these two functions are slightly different. And this slight difference is coming from because the fact that the line of sight distance are always biased because of this peculiar velocity. And at large scale, what you'll see the impact is they are basically infalling. The galaxies are infalling with each other. So what you'll see is that you'll typically estimate distance is smaller than what it should be, right? And if you imagine something like that, and if you make a plot of that in 2D, you'll get this picture. So this is essentially two-point correlation function, which is counting pair of galaxies as a function of perpendicular distance on the x-axis and parallel distance on the y-axis. If there was no redshift space distortion, what you'll find is that this will be a circular pattern. So it's isotropic. But what we see is it's not isotropic. And this strength of anisotropy depends on what is the strength of velocity. And so if you measure this, which you can measure in a galaxy redshift survey, you can measure strength of gravity, and hence you can check if this strength of velocities are consistent with what you would expect compared to gravitational redshift. Compared to what is the prediction of general relativity given the initial condition of the universe. So this is the phenomena. Not sure if that answer your question.
Yeah, I quite didn't know what the origin of it. It's because of the peculiar velocity of the galaxies, is it?
Sorry, can you say that again? Something about peculiar velocity.
No. So the redshift space distortion is an effect of the peculiar velocity of the galaxies, is it?
Yes, that's right.
Yeah.
Okay, so in the beginning you were talking about a little about work-life balance during PhD and later. So like if you could talk a little more about it and like your experience.
Yeah, sure. I'm happy to. I think as an undergrad, we are really surrounded by friends and we are living in hostel. So we never think about things like this. But once you go to a PhD, you're already old enough. I mean, I'm pretty old now, I guess. You're already old enough and you're not living in the similar kind of environment. You're most likely living in an apartment with a few flatmates or maybe just by own. Either you're working or PhD in either case, right? And you're working, most likely you're not even living with your parents these days, just because you have to move to a different city or different country. And so at that time, if you're not conscious about things like this, it start to feel very isolating. If you're not investing time in yourself, if you're expecting that these things will happen naturally as it happened in IISER or like undergraduate time, just because the environment was very different, it doesn't happen. And so when I moved to US, I did feel quite isolating and lonely. And then the only thing I could do is essentially spend all my time working on things like courses or research and things like that. And there's quite a lot of things to do, so you can spend a lot of time. But over the time, it kind of burns out. It weighs on your mind, and because of that, you start feeling low, right? And it's difficult in various ways. So I felt like what helped me is starting to get taking our time consciously, like saying, okay, no, this is the time when I have to spend on some sports or something else. For personally, in my case, I started playing squash and a little bit of tennis, but mostly squash on a regular basis. Going to gym a little bit on a regular basis and for a walk. And also spending time making sure I talk to my family on a regular basis. That helped me a lot. Making sure I don't work on weekend. Yeah, for example, right now I'm working kind of talking to you guys on weekend, which is difficult for my son. But making sure I don't work on weekend. These kind of decision you have to take consciously, and I feel it's very important to be aware of before you get into that situation, so that you don't spiral down too much and have difficulty really coming out. So consciously thinking about work-life balance is important. I'm still struggling to do this, especially right now with coronavirus when I'm at home all the time. But I feel like I'm doing better now compared to what I was doing a while ago.
Thanks a lot.
Sure.
So you had mentioned that you are working on the dark energy survey and you had previously worked on the SDSS.
Mm-hmm.
So I had read online that the after that SDSS is the legacy survey or something like that. So what's the difference between the legacy survey and the dark energy one? As in the capabilities.
Oh, okay. So legacy survey is, legacy is, I guess you understand what the legacy means. So legacy is essentially just that it has a long-term value, right? And so I would not say that DESI is not legacy and is just legacy. SGSS, in terms of capability, if you want to think about, then you should think more in terms of what is popularly known as SDSS is a stage 3 survey. DESI is a stage 4 survey, something like that. And so in terms of capability, there is a huge difference. What SDSS took 11 years to measure 2 million spectra of bright galaxy, DESI is going to take 5 years to measure 35 million spectra of much fainter galaxy to much farther distances. So you can see the capability is completely different. But it has nothing to do with the legacy or not. It's just that SDSS is done already. DESI is something coming and in the future, and DESI will have a lot of legacy value once it's done. Does that answer your question?
I meant about the legacy survey of the LSST survey. I think it's called.
Oh, you mean LSST survey? Okay. So what is the difference between LSST and DESI?
DESI and LSST, yeah.
Okay, yeah, that's a very good question. So LSST is a much bigger telescope. It's 8 meter compared to DESI being 4 meter. LSST is a brand new telescope. DESI is a old telescope with brand new instrument. But the major difference between LSST and DESI is that LSST is what we call photometric survey. So you remember initially I talked about taking images. So what LSST is going to do is simply take images of sky at various parts. Of course, it's going to be beautiful in terms of depth and quality and precision, but it's going to just take images, which means it's not going to have capability to measure spectra, and hence how far these galaxies are. Line of sight distances of these galaxies, something you can't do with LSST. The prime focus of DESI is really to measure spectra, so it's not going to take any images at all. So there is no CCD in DESI instrument. It only has optical fiber. So what DESI already need an imaging survey, something which has already been done. And then from that imaging survey, it selects, okay, these are the galaxies I want to take spectra of, and then it takes the spectra. So before DESI, another photometric survey is already being done, which is what it's using to take spectra. But if you were to think about main differences, one is a spectroscopic or galaxy redshift survey. One is a photometric survey, which is just taking images. And then the telescope instrumentation is completely different because one is taking fiber spectra, one is taking just CCD images.
Thanks.
You had recently written a paper with Dr. Paranjape about using Voronoi tessellations to see how the dark matter halos in galaxies kind of seeded. Could you talk a bit about that?
Mm-hmm. Yeah, sure. So I talked a bit about two-point correlation function, which is interesting and nice, and it has lots of precision. But if you think about a complex distribution of points, and if you're just looking at two-point correlation function, you're looking at only particular moment of it. So if you're familiar with Gaussian distribution, you know that for the Gaussian distribution, once you know the standard deviation or mean and the standard deviation, all the higher order moment is perfectly known, right? But if you take a skewed distribution, something like chi-square distribution, then it has mean and standard deviation, but it also has a skewness and it has a kurtosis and blah, 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 right? It has a higher order moment. So when we look at the structure in the cosmos, when we look at the structure in the galaxies, especially at late time, we know that it's the structure is not Gaussian, which means if you just measure two-point correlation function, that's equivalent to measuring sigma. But what about kurtosis? What about skewness or the higher order moment? So there's information in the structure of galaxies which we are not seeing by two-point correlation function. And so there are various techniques to actually try to extract these information, which is in higher point, what is called higher point functions. And Voronoi volume tessellation is a scheme, or it's a measurement technique which we developed, which we thought is powerful because of its simplicity, but it's also sensitive to certain aspect of dark matter distribution. For example, what's the nature of dark matter? Whether it's a cold dark matter or warm dark matter is going to imprint, have a slightly different this higher point function, which you can measure through VVF, what called volume tessellation. So there are several other things which you can do other than VVF. For example, you can measure voids and structures around voids. That is also going to be sensitive to these higher point function. But the basic idea here is that you want to go beyond 2-point function. You want to measure a more complex structure because there is information, and see if that can help you infer either understand either the questions about where are galaxies with respect to dark matter, or what is the nature of dark matter. And depending on what theoretical model you're looking at, different things are useful, and we found that VVF is very useful for looking at this galaxy halo connection and the nature of dark matter based on some of the simulations we have looked at.
Thank you.
Yeah.
Shadab, you did a lot of projects at IISER. So was there a time when you were confused as to what you were actually interested in, and you weren't sure where you were going in your research, and how did you manage to overcome that, if any, confusion?
So personally, I must tell you, when I joined IISER, I didn't think that I will go for PhD. Also, I was not trying to develop a research profile, so in that sense, I just wanted to do what I find interesting, and I also wanted to explore various fields. So in that sense, that question didn't came to me that where I'm going. I was just exploring things and having fun to an extent, and making sure my academics are going okay. That was my focus. But towards the end, like in my during my master thesis, I did give thought about questions on this angle, and I felt like among the several projects I've done, many of them has a common theme, and that common theme was aspect of theory and aspect of computation, right? So I felt like, okay, this is really something I love. I love solving some problem by pen and paper, analytics and computation. So some sort of simulation or coding is something I enjoyed from the beginning. And so we actually had a course on MATLAB in the first semester. I don't know if it's anymore the case, which was what introduced me to a lot of programming and things like that. Yes, I did end up thinking about this in my 5th year, and I felt like I wanted to do something which has to do with some sort of data and computation, which is why I joined CMU, and because that has a very strong computing background. So you will get exposed to a lot of computational technique and all sort of things. As well as my project, which I was working on, radio astronomy, which is also very heavily computation based. I was learning to program in Fortran during that time. That is something I could have continued at CMU if things would have worked out slightly differently.
Okay, thank you.
Okay, so if someone doesn't want to do a PhD, then then what kind of profile does he or she should make, and how to go about making that profile?
Yeah, thanks for this question. First of all, I must say that I'm not an expert on this thing because I end up doing PhD, so probably I'm not the best person to answer this question, but I'll still tell you what my beliefs are, which might be completely biased and nothing to do with reality. Is if you want to, first of all, let me acknowledge, given a science degree and not having a technical background, it is hard to find an industry job for sure. So don't be disheartened, it's going to be a bit difficult. but it's not something impossible. If you plan in advance, if you start planning in end of your 4th year, I think it's definitely feasible. In terms of what kind of profile, it also depends on what kind of job you want to do, and there's a wide variety of job possible, right? For example, if you want to go into insurance company model, right? There's a whole lot of framework developed for that, and it's called IFOA, Institute for Actuarial Training. And what they do is they have series of exams. So you just have to start clearing those exams, which are mostly mathematics and probability statistics and things like that. If you just start clearing series of the exam, which happens, I think, twice a year, you'll automatically get a job in that sector. So if you are interested in that kind of thing, any sort of thing which has a professional body, right? So look for that professional body and see what kind of a scheme they have. Most of the professional body, either in finance or CA, they have a series of exams which you can start giving and preparing. And if you clear like first few set of exams, you'll get a job as a trainee, and then more you clear, higher you go in thing. But if let's say if you're interested in a field which does not have a professional body, then you really need to ask somebody in the field who is working in the field, like try to find a contact person who is working in the field and see what skills are needed. Of course, as a blanket term, I can tell you that these days, if you have coding skills, then there's a lot of jobs which is interested in that. But that's not necessarily true for a specific field. For example, for an actuarial job, you don't necessarily need coding to begin with, but you need these mathematical skills and clear these exams, which eventually will require coding at the end of the day. I think the best way to prepare is starting thinking a little bit about what might be interested in, or at least what you think you'll be able to do it easily. See if there's a professional body. If no, then try to find a contact person, either through a alumni or you can directly contact people on LinkedIn and see what are the skills required and try to develop those skills. And I don't think there's a one set of skills which covers pretty much everything. It really depends on what kind of job profile you're interested in.
So for example, like a space related non-academic job, like it is a thing now, like with space companies and like
Right.
So for this example, like what kind of profile or like what kind of project?
So for space related non-academic job, there are few categories in that. There are categories of essentially people who works in the space observatories or around space missions, right? And a lot of that is administrative job. There's a lot of private company coming up these days who is analyzing space data and giving information, like having clients telling them, okay, for example, what is the forest coverage in certain part of the world and things like that, or following things live. I think there are a couple of companies recently launched as a startup in India. But in general, if you want to go on the space data analysis side, then of course coding and these days machine learning techniques are very important. In fact, I have a friend who is a IISER alumni, Belul Sabir. If you want to get in touch with him, he's right now he's working in space, more like finance related things. But he was also considering. He had some offers from this space-based companies. So I think for space-based company, if you want to go on the data side of things, then the answer is get skilled in machine learning and programming. If you want to go to administrative side, then that's a longer route, and generally they hire people who already have PhD. For example, NASA has lots of employees who already have PhD and know a little bit more about astronomical data analysis. So having a PhD in a field which involves astronomical data analysis will let you enter in a non-academic job for a space-based industry, which is not data analysis.
Okay, just where can I find that friend of yours you were mentioning?
I can send you, if you drop me an email, I can connect to you with him.
Okay, sure. Thanks a lot.
Sure.
Hello. Yeah,
Hi.
this is Ajay. Yeah, so I want to ask what are the possible jobs for a radio astronomer in non-academic field?
Sorry, what is the possible job for?
For a radio astronomer in non-academic field.
Radio astronomer in non-academic field. So radio astronomer, if you are, so radio astronomer is generally, you'll be doing both observations and analysis, but most of the radio astronomers spend most of their time doing analysis, and these are fairly complex analysis. So I think given their skill set, they will be perfectly suitable for anything related to from data science to finance. Their skill set is very aligned to that kind of field, but it doesn't mean you can directly get into that. You still have to invest and learn a little bit, or let's say if you want to get into finance, you have to spend a couple of months and learn a little bit about what sort of algorithm they are using, what sort of problem statements they are working with to actually crack the interview for these jobs. But I think that's definitely a place where you can move in with little effort. Broadly speaking, data science or finance kind of area.
Yeah, thanks.
If there aren't any more questions, I think we can end the talk now, and thank Shadab for this great interaction. So, yeah, is there any more question? Okay, so I think.
So can we have your email ID? We'd like to communicate with you sometime later.
Yes, sure. So if you can still see my screen.